So in this class, let us see about the various types of parameters such as distributed parameter and lumped parameter. So the given property of the model is assumed to be concentrated into a single element is known as a lumped parameter models. So for example, in lung mechanics model, the total resistance of the central airways is lumped into a single quantity RC, even though in reality the central airways are comprised of the trachea and a few branching generations of airways, each of which has very different fluid mechanical resistance. Similarly, a single constant CL is assumed to represent the compliance of the lungs, even though the elasticity of lung tissue varies from region to region. In order to provide a more realistic characterization of the spatial distribution of system properties, it is often used to develop a distributed parameter model. So this kind of model generally takes the form of one or more partial differential equations with time and some measure of space as independent variable. So in distributed parameter model, this can be viewed as a network of many infinitesimally small lumped parameter submodels. To illustrate this relationship, we will derive the governing differential equation of a distributed parameter model of the passive cable characteristics of unmyelinated nerve fiber. So the nerve fiber is modeled as a network containing serially connected multiple subunits, each with circuit elements Rx, Rm, Cm. The Rx represents the axial resistance of 1 centimeter of nerve tissue per centimeter square of cross-sectional area and is given in ohm centimeter. RMCM represent the resistance and capacitance of 1 centimeter square of nerve membrane surface area respectively. So this we assume that the extracellular medium bathing the nerve fiber represents the electrical ground in this model. So in the distributed parameter model, the partial differential equation describes the transfer of force from the constitutive equations, whereas in lumped parameter, the analysis is at the component level. The component properties are self-contained and complete. So the equations are solved analytically or numerically in the lumped parameter models. So in the distributed parameter model, the physically there will be better descriptions and the results are more accurate when it is done correctly. So in the above example, the nerve fiber takes the form of long cylindrical conductor of radius A, and we focus our analysis on a small length del X of this cable that contains one of these resistance capacitance subunits. So the lumped parameter descriptions are appropriate when the property being examined is of much greater magnitude than the added accuracy that would be gained using a distributed parameter model. So in the one-dimensional cable equation, it describes the intracellular voltage along the nerve fiber as a continuous function of length and time. So here are some of the lumped parameter variables. So for an example, in an electrical system, current, charge, voltage difference, flux linkage are the lumped parameter variables which can be named as variable through element, integrated through variable, variable across element, integrated across variable. So in the same way, the mechanical, translational and rotational systems and also fluidic and thermal systems are also explained in terms of lump parameter variables.